All right, so this is a sort of culmination or the finale of the course here. We have done all the amplifier stages, both bipolar as well as MOS. And in the next, I think we have 3 lectures left, including today's. So in the next 3 lectures, what we'll do is put a couple of stages together, differential pair, common emitter, gain stage, common collector output stage, put all of them together and make an operational amplifier. All right, so let's continue then. What we are discussing is then a BJT operational amplifier. And I would like to emphasize that this is a very simple BJT op-amp design that we look at. It's almost like a toy op-amp, okay? And after going through the design, we'll see that the op-amp that we make is unstable under closed loop conditions here, and we need to compensate it. Something that you've done, I'm sure, a lot in EE210, the control systems course here. And then once our op-amp is ready, then we'll take our op-amp and make some very simple circuits like non-inverting amplifier and buffers and things like that, and see how well our op-amp works here. So the specification for our op-amp is as follows here. As I said, this is a very modest op-amp. What we are trying to do is build an op-amp with an open loop gain of 10 to the power 3, input resistance of 100K, and output resistance of 100 ohms here. And most of you are aware of the specifications of the 741 op-amp, where the gain would be around 10 to the power 5, input resistance would be mega ohm, output resistance will be in tens of ohms here. So as I said, this is a very modest specifications, but the idea is to see how one can build a multi-stage amplifier to satisfy these specs here, okay? And we'll assume that our supply voltage, our op-amp will run on plus minus 12 volt here. Okay. Further, in order to simplify, note that if you want to build high gain, it's best to use an active load. And it's easier to build high gains using active load here. But again, I'm going to avoid that in this particular simple op-amp here. And the general architecture of an op-amp is shown over here. Most op-amps will have at least 3 stages here. The first stage is a differential stage here. And the goal of this particular stage, as you can see here, is to provide the required input resistance. So the burden of satisfying the input resistance is on the differential amplifier. The burden of satisfying the output resistance, R0, whatever R0 is on stage 3. The last stage here, the output stage here. And both the differential amplifier that we use here, as well as a gain stage that we use here, both of them together have to provide the gain that you see here, overall gain here. The last stage is an output stage. We'll use a common collector whose gain is 1. So all the gain has to come from stage 1 and stage 2 here. So what our op-amp is going to look like is a differential pair here, and a common emitter stage here, and a common collector kind of a stage here. Okay. So let's go ahead and see how one can design each one of these stages, put them all together in order to satisfy these specs here. All right. So diff amp, common emitter stage, and a common collector stage here. So this is our starting strategy here. We'll see whether it helps or not, or whether we succeed in satisfying the specs using this kind of an arrangement or not. All right. So let's start with a differential pair. So this is the differential amplifier that we have. As I said, we are not using an active load. We're keeping it simple. So we have biased through a current source. And I'm not going to talk much about the current source in this. We know current sources are fairly easy to build. All you have to do is use a transistor here and another transistor in the form of a current mirror, and one can easily build here. So I'm going to omit this particular part here. Okay, how to build the current source here. All right, so if we look at this particular stage, as I said, this particular stage has to provide the input resistance that I require. And input resistance that we are talking about is a differential input resistance here. And input resistance is then, we know from an analysis of this amplifier, is 2 R pi. And 2 R pi we know is 2 VT. thermal voltage divided by ICQ1, the current here, multiplied by beta. So that's 2R pi. And our specs tell us that we need an Rin of 10 to the power 5, 100 kilo ohm. So what we see is that then, given this expression, beta throughout we'll assume 100. So BT we know. So it immediately gives us ICQ1, and it tells us that IEE, which is twice of ICQ1, is 0.1 milliampere here. So the biasing of this stage here, the current, is determined by the input resistance here. Whatever input resistance you require, that immediately determines the current that needs to flow here, and that determines the overall current IE here. All right, so that's the input resistance. If this specs had been 1 mega ohm, then you can easily see that the emitter current would have become 0.01 milliampere here. So the emitter current, this current here, would have fallen by a factor of 10. All right, so this is the current then. So it looks fairly easy that we can satisfy the input resistance specs by simply choosing the current to be this one. All right, let's look at how do I choose RC. In this differential pair, there are only two choices that you have. One is the current here, and the other one is RC here. Of course, there's a choice of the transistor also, but transistor characteristics have already assumed that the beta is 100, early voltage is 100, so a transistor is given. So it's not a part of the design. Okay, so RC we know that influences my differential input gain here. And ADM we have seen is 0.5 GM RC here. So V0 by differential voltage here, V1 minus V2 is 0.5 GM RC. And GM we know is ICQ1. So ADM is 0.5 ICQ1 RC by VT here. So ICQ1 is fixed. So effectively we know that the differential mode gain of this stage is decided by the drop here. ICQ1 RC is this particular drop here. And if you want a large differential gain, then you should try and build the drop here as large as possible. So the issue is, how large a drop can I make here? Now note that as the drop increases, the collector voltage falls. And as the collector voltage falls, if you're not careful, the transistor may go into saturation region here. So you have to keep the collector emitter voltage sufficiently large in order to avoid transistor going into saturation region here. So how large can I make? Well, if I look at the biasing, when I look at the biasing, these two inputs are ground. This voltage is minus 0.7. Okay, approximately minus 0.7. And I need to maintain this particular transistor in saturation region. Now, it's not simply that you have to keep this voltage here 0.2. Because note that as you apply your input voltage here, there will be a swing also here. And therefore, I must have collector emitter voltage here, which is sufficiently large in order to allow that much swing. But note also that this is the input stage here. There's an input stage here, and then there's a gain stage, and then there's an output stage here. So the swing at this particular point will be small. Okay, swing at this particular point will be small. So what I'm assuming here, coming back, I'm taking a reasonably small value of collector emitter voltage, which is 1 volt. Okay, it is slightly arbitrary. You can take a little bit smaller or a little bit larger also. But we note that VC1 equal to 1 volt should be sufficient to keep it out of saturation region. And as I said, the swing here is not very large, and therefore this value should be reasonable here. So if I assume collector emitter voltage between these 2 points to be 1 volt, it's telling me this voltage will be plus 0.3. And therefore, we know now that the drop here, this drop here that you see here across this particular one is going to be 11.7. The drop here is going to be 11.7 here, and 11.7, which means ICQ1 times RC is 11.7 here, and therefore it tells us that one can build a gain as large as 227 here. 227, and since I know ICQ1, so if ICQ1 times RC is 11.7, and I know ICQ1 already, because ICQ1 is here, half of 0.1 milliampere here, so I know the value of RC, which comes out to be 227 kilo ohms. Alright, so the way we determined RC then is, we chose a value of VCE to keep the transistor out of saturation region, and then we try to maximize the drop here in order to build a gain as large as possible of the first stage. Okay, so we obtain a value of RC here. So we have a design of differential pair which is complete. We have the current and we have the value of RC. Alright, we'll see whether this is a right choice or not, because note that your interest is not simply in designing a differential pair. Your interest is in designing the overall op-amp. Okay? And sometimes what is best for a differential pair may not be best for the overall op-amp. Okay? All right, so this is my differential pair design here. Note that the bias value here is 0.3. Okay, next thing is I'm going to connect a gain stage, common emitter amplifier here. So the common emitter amplifier that I'm connecting is over here. And you'll see in a minute that I need to keep RE here. I need to keep RE here. The reason being is, note that this common emitter stage will be connected to the previous differential stage here. Here, if you look at this particular picture here. Now, if I don't, note that this value was 0.3. If this value was 0.3 and you don't keep your emitter resistance here, then if this is 0.3, this one would have become 0.3 minus 0.7. So it would have become something like minus 0.4. But we know that the negative supply voltage is minus 12. So it's not possible. You cannot satisfy the biasing requirement if you simply leave RE2 out. So you need to have an emitter resistance here. You need to have an emitter resistance in order to allow that much voltage drop here. So I need an emitter resistance, and collector, of course, has to be there in order to build the gain here. So that's why RE has to be there as part of my common emitter. And note that I cannot bypass it because we are building an op-amp. Op-amp is entirely on chip, and I cannot put a capacitor here to bypass. So RE2 will be there. All right, so the issue is, we said that this is 0.3 because we had said this drop is 11.7. Sorry. And as I said, you have to keep RE2. So let's look at this particular part of the design in a little bit more detail here. This half here. Okay. So this only, I'm drawing only that part. The remaining part I'm leaving it out. So this is 0.3. And gain of this particular stage here. So we are using a common emitter stage in order to build a gain as large as possible here. So gain of this particular stage, all of you know, is equal to GM divided by 1 plus GM RE2 multiplied by RC2 here. And GM RE2 is large, so you can approximate the gain as RC2 by RE2 here. It's basically the ratio of the resistance here and the resistance here. Also, if you note, I can also write it as follows here. Since it's the ratio of the resistances here, the current flowing in this branch is almost the same as current flowing in this branch. Collector and emitter currents are almost same. So I can also say that the gain of this particular stage is the ratio of the voltage drop here and the voltage drop here. Okay, the two drops, the voltage drops here. So you would like to keep these voltage drops large, the ratio here. Can we do that? Well, let's see. Let's do a quick analysis here. Note that if this is 0.3, then there's a 0.7 volt drop here. So this is minus 0.4. This is minus 0.4. And I have to keep Q2 also in saturation region, out of saturation region. So, you know, it's a little bit aggressive design here where we have chosen this as approximately 0. So if this is 0, then collector emitter voltage is 0.4. It's 0.4. It's larger than 0.2. So transistor would be in saturation, will be in active mode, but just at the edge here. You can, you know, make it maybe a little bit, increase it to 0.6 also. You can put it 0.6, and then this will be about 1 volt, maybe a safer design. But the point is, you'll see that in a minute here. So if you're very aggressive, you'll set it at 0. And then this drop here that you see here, the drop is 12 volt here. And the drop here, minus 0.4 and minus 12, you see the drop here is larger than 12 here. So what you are seeing is that you'll get no gain. You have put this common emitter stage for the purpose of building gain, and you're saying that for the design that we have, I cannot get any gain from this particular stage here. The ratio of RC2 by RE2, you can see here the drop here and the drop here, the ratio will be close to 1 or even less than 1 here. So the trouble then is that either I modify this design here, I go ahead and note that differential pair was designed with the objective of maximizing the gain of the differential pair. And when I maximize the gain of the differential pair, I set it to 0.3 to get this drop as large as possible. Then I find that I cannot build any gain in the next stage. So so one can go ahead and modify the design of the differential pair so that one gets a gain here. So eventually what will have to happen is you reduce the gain here, and then you'll get a higher gain maybe at this particular point here. But then at this stage, maybe what we can do is we can even try a PNP stage here. Okay. When you interface an NPN and a PNP here, NPN base differential pair, and if the next stage is also an NPN stage, you are seeing the trouble that is occurring is you have 0.3 here, and we don't want RE2, but then if you don't want RE2, then this node gets connected to -12. If this is -12, then this transistor is not biased. It cannot get biased, okay? So the trouble is occurring because I have a base emitter drop here. So the idea is, what if I take this Q2 out and substitute a PNP transistor here? Then between the base and this node, I will not see an emitter, but I'll see a collector node. Okay, so that's the motivation for trying out a PNP stage. So we take our NPN gain stage and we replace it by a PNP gain stage. So emitter is here and collector is here. All right, so let's try this out. Let's see if this works fine. So again, all right, so this is our PNP stage here. Now let's go forward and complete the op amp also. Suppose this works fine. Then the next stage is, after that, so this is differential pair, this is the gain stage, and the next stage is the common collector output stage. So it's a common collector amplifier. The purpose of this amplifier is to provide you with low output resistance here. And we had seen earlier that common collector amplifier is best built if you bias it through a current source. Okay. So this then looks like a simple op amp, but let's see whether it can provide us with adequate gain output resistance or not here. So now note that if you're making an op amp, when you don't apply any input here, which means this is ground and this is ground, what you require is that the output should be 0. Okay, so we assume that if no input is, when looking at biasing, if no input is applied, we assume that this is 0. We want it to be 0. If this is 0 here, then this voltage is 0.7 here. Okay, that is deciding that this voltage has to be 0.7 here. All right, so let's come back then and see whether one can get a gain from this particular stage or not. So we come back to our stage here, PNP stage here, and I'm not doing a very exact analysis. This is supposed to be 0.7. Just for quick analysis, I'm assuming that this is very close to 0. Okay, that's what it means here. So this is very close to 0 here. Now, gain of this particular stage is also RC2 divided by RE2. RC2 here and divided by RE2. Also the same as voltage drop here and the voltage drop here. So if it's the same thing as voltage drop and these two nodes here. So if I look at the voltage drops, what I find is this is 0.3 here. So the voltage at this node is 1.71 here. So the voltage drop here is 11. The voltage drop is 11, which is this delta VE here. And the voltage drop here, this is 0 and this is 12 here. So the voltage drop here is 12. And therefore, we again get a negligible gain. So we went to a PNP stage thinking that, again, you may be wondering, I cannot connect this node directly to 12. I need a RE2. So all this problem is occurring because I don't have a bypass capacitor, or the biasing of this stage is getting decided by biasing here. So the two are coupled together here. If we had a capacitor, we could have put a capacitor here so that DC value from here doesn't propagate to the output here, and things would have become simpler. But we can't do that, and that's why you note that these problems are occurring here. So the issue then is that I'm getting a gain here, but I'm not getting any gain at this particular point here. So what we do then is we go back and modify the design of the first stage. So the idea is as follows here. The idea is as follows. So right now we're getting a large gain, some 230 or so large gain here and no gain here. So let's look at now both these stages together. Earlier what we were doing was taking the differential pair and designing it independent of the next stage here, and trying to maximize the gain of the differential pair itself. But note that it's not the differential pair that you have to optimize, but you have to optimize both of them together. So let's look at both of them together and see how large a gain can be built here. So the idea is, if I look at both of them together, the first stage gain depends on this drop here, the voltage drop here, which is delta VC1 by VT. The second stage's gain depends on the drop here divided by drop here. That's AV2 here. Now, when you build bipolar amplifiers, there's also a trouble that the second stage may load the first stage here. So when I look at this particular node, I'm seeing not just RC here, but I'm also seeing the input resistance of the second stage here. So actually, this equation is not really correct, unless you take a precaution that the input resistance of this stage is much larger than RC. If you do that, then you can write that total gain is going to be AV1 times AV2. Otherwise, this input resistance also comes in parallel with RC, and therefore the gain of the first stage will fall there. But we are assuming that we'll choose the values in such a way that the input resistance here will be larger than RC. We are assuming that we'll do the design like that here. In that case, the overall gain of this particular stage will be AV1 into AV2, which means that this stage will not load the first stage here. Now, this, as I said, this part is fixed for us. Why is it fixed here? Because go back and see that when we went here, we are going to use a stage like this. So we want the output to be 0. And if the output is 0, this part is about 0.7. Okay. So we can't do anything about this particular node here. All right. So that's why I'm saying this drop is approximately 12 here. You can't do anything about it because this voltage is close to 0 here, 0.7 or so. So this is about 12 and is a constant. So delta VC2 is fixed for you. What you can do is you can alter the drop here, and as you change the drop here, this drop will also change. Because note that as you change the drop here, what happens is this voltage changes here, and any change in this voltage is reflected by a change in this voltage here, because they two are related through a 0.7 volt drop here. So now you can play around with these two drops here. You can decrease this and you can increase this or decrease this also. Okay. So what we had was the present design that we have is we had chosen this to be 0.3, and so the whole drop was 11.7, and so this drop was 11.7 here, very large drop. So the gain was 0.5, 11.7 divided by VT here. But as we do 0.3, we get a voltage here 1, and so this drop becomes 11 here. So I get 12 by 11. So the gain here is only 245. Now what we are saying is alter the drop here and thereby alter the drop here. I'm showing you one possibility, that suppose I make this drop now 1 volt. It's totally opposite, right? Here the drop was 11.7. 11.7 here. Now I'm saying make this drop equal to 1 volt. Suppose. Then note that the gain of the first stage will become 1 by VT. And if this is 1 volt here, then the voltage at this point is 11. The voltage at this point is 11, and the voltage at this point becomes 11.7. And if this is 11.7 here, the drop from here becomes 0.3. And therefore the gain of this stage becomes 12 by 0.3. So the gain becomes actually 770. So note that here I'm not designing my differential pair to have the highest gain. If I do that differential pair with the highest gain, then I'm not able to build any gain in the second stage. All right. So that's what I said. Individually, if you take each stage and make it the best possible and you put them together, overall it would be inferior. You have to look at the whole thing simultaneously. So I've just given you one design here where we make this around 1 volt drop here, and we'll get 0.3 here, and we may get a gain of 770. All right. It doesn't satisfy our requirement of 1000, but it looks like a promising design. Maybe you can see here, if you want to push the gain further, what you'll have to do is maybe reduce it a little further here. And as you reduce it a little further here, instead of 0.3, it may go to 0.25 or 0.2. Okay, it may here. All right, so that's how I can push the gain further to 1000 also. All right, so at this stage, what we have is a gain which is reasonably large, 770. And therefore, what I'm going to do is take this particular design and go forward and see how does my op-amp really work here. So note that the gain of the first stage is 38, the gain of the next stage is 40 here. So it's more like a balanced design with equal gain here and an equal gain here at this particular point. All right. So we are going to choose this point here. Again, note that if this drop is 11, so this voltage is, if the drop is 1, so this voltage is 11 volt here. So we're going to choose this as 11. And so the gain of the first stage and the second stage we've already seen here. Now, if we choose it to be 11, then the voltage here is 12. So 12 minus 11, 1 volt drop here. And we know the current that flows in this RC. Current is nothing but 0.1 milliampere divided by 2. So we get a value of RC, new value of RC, which is 20 kilo. Okay. Keeping in mind this voltage drop here. So this is 20K here. Now the next thing is, how do I choose RE2 and RC2? Now we know that the gain of this particular stage, as we said, is about 37.66 here. And if I know the gain of this stage, so if I know RE2, then I'll determine RC2 here. So the way I do it is as follows here. We said that we would like to prevent this particular stage from loading the first stage here. So we would like to make the input resistance looking from here much larger than 20K here. Okay, and if you look at it from this side, the input resistance is R pi multiplied by beta times RE. And R pi in general will be smaller than beta times RE here. So we approximate the input resistance as beta times RE2. And this resistance, we want it to be much larger than RC here, 20K here. So therefore, this tells us if beta is 100 here, if beta is 100 here, then we want RE2 of 200 ohms is good enough, right? A factor of 10 higher. Okay, if I have 200 ohms here multiplied by 100, so that's sufficiently large as compared to RC, at least a factor of 10. So we choose RE2. RE2 should not be much larger than, I would say, 200, but we choose RE2 close to 200 ohms. Okay, so RE2 should be much larger than 200 ohms. So we choose RE2 a factor of 10 higher, which is 2K. Okay, so RE2 is chosen as 2K, which will help us build enough input resistance, and therefore this stage will not load my first stage here. If I choose RE2 equal to 2K, then I get a value of RC2 immediately from this ratio here. So we get RC2 equal to 75K. So that's how we end up getting the design of these two stages together here. Let me show you, so at this stage, let me, while you're doing your design, it's good from time to time to take the circuit and simulate, because you're making various approximations. Note that the gain is not exactly equal to RC2 by RE2. The voltage drops that you see here are not exactly 0.7. Okay, so there are going to be changes when you simulate the design here. So the same design has been taken and simulated, and one gets a gain of the first stage 17.2. Overall gain one gets 593.6 here. Remember, we were hoping a gain of, how much was it? 700. I think gain of around 700. But note, 700 was, we simply took gain of first stage multiplied by the second stage here. This stage is going to load the first stage here. Even though we have chosen input resistance, which is a factor of 10 higher, but factor of 10 means at least 10% change will be there in the first stage. Okay, there is going to be loading here. So the simulation then shows us a gain of 593, close to 600. So, well, input resistance is 116 is fine here, but the gain is low. In fact, to begin with, we were hoping for a gain of 700, and the gain has further decreased to a value of 600. So we need to do something about the gain here. Output resistance, note at this stage, is 75K. But there's further problem here. The further problem comes from the following fact here. So right now, as I said, I don't want to go and optimize this particular stage further, because there is a next stage also sitting there. And the next stage is going to influence my previous stages also. Okay. So the next stage is a common collector stage here. And common collector stage also has to be biased at a certain current. So the issue is how much current should I bias my common collector here. Now, I'm going to assume, so output voltage is 0, as I said here. So I'm going to assume that my load resistance is going to be larger than 1K. I'm designing it for 1K or larger load resistance. And note that if you want to have a swing, your supply voltage is plus 12 and minus 12. If you want to have a swing of plus minus 10 volt, then you know that the product of the current times RL should be greater than 10 volt. Greater than or equal to 10 volt. Here from the swing point of view, we know that this IE3 times RL should be at least 10 volt, and the minimum RL for us is 1K, and therefore I must have a biasing current of at least 10 milliamperes. So 10 milliamperes multiplied by RL gives me 10 volt here. So with this kind of a current, I would have sufficient current in my amplifier to build a swing of plus minus 10 volt. So that's why I choose 10 milliamperes as the biasing current. Okay. Now, so this is our op-amp. This is how it looks. 20K, 2K, 75K, and 10 milliamperes here. We bias it here. So now the trouble is, when you look at the output resistance from here, All of you know now the output resistance when you look from here is R pi plus whatever is the resistance in this base here. And what is the resistance in the base? When you look left, what do you see? Between the base and ground, what do you see under small signal? 75K. Between this node and ground, this will become small signal ground, and you see 75K here. So the resistance looking from here is 75K here. So your output resistance is approximately, when you look at it from here, R pi is small, so don't worry about it. R pi plus 75K divided by 1 plus beta, so that's 742. And remember, our requirement is 100 ohms. We want an output resistance of 100 ohms here. So we immediately fail in our output resistance here, fail by a large margin, a factor of 7 higher than what we require the value here. So now, so this is what it's telling you is, if you want a lower output resistance, what do you have to do? You'll have to lower this. If you lower this value, then note that the gain of this stage is nothing but the ratio of this and this stage here. So if you lower this value, then you'll have to lower this value here. If you lower this value, what happens to input resistance? Becomes smaller, and it starts loading my first stage here. So you can see that they're all coupled together. So we have, at this stage, it's difficult for us to supply the output resistance that you see, which is 100 ohms here. So this is 11 here. There's further problem that occurs here when you put this stage here. See, this is 11. We had set it to about 11 here. And when you set it to 11, this voltage is around 11.7. So you have a current which is 0.17 milliamperes here. Now, when you have 0.17 milliamperes current here, now we were thinking that this entire current will flow here. But now when you put this stage here, and note what is the emitter current? 10 milliamperes here. So what is the base current of this stage? 10 milliamperes divided by 100. So which is 0.1 milliampere here. So 0.1 will go there. And so this actually 0.085 goes here. And so this voltage, now it upsets, we had assumed that this will be 0 and this will be 0.7, right? But we didn't take into account the fact that there's a base current that will flow into this particular stage here. So we actually find that this voltage is minus 5.5 and this is minus 6.3. So when I put them all together, when I put ground here and a ground here, what we find is that the voltages at this node is minus 6.3 and I want 0. Okay. So that's the trouble occurs because of this base current that flows in there. All right. So this is the simulation result that we have here. So it's showing us minus 6 here and minus 5.5 here and all that. Okay. So now I want to bring this minus 6 to 0. Okay. How do I bring minus 6 to 0 here? What do I do? Well, I don't want to touch this current here. That current is needed to develop swing. Now, what I'm going to do is I'm going to fine tune this particular resistor here. Can you see that if I change this resistor, this voltage will change, obviously. And as this voltage changes here, this will also change. So now, should I make it higher or lower? Some current is going here. What should I do? Make it higher or lower? I should make it higher. Note that if I make it 160K, then what happens is by making it 160K, I bring this node to around 0.7 and the output falls to around 22 millivolt here. Now, something interesting happens here. So while I bring this particular node to 0.7 and this comes to 0 here, I've increased the value of RC2. And gain depends on what? RC2 divided by RE2. So as a bonus now, once I do that, I get a gain which is 1000. So by this design, I had a gain of 567 and the output voltage was also poor here. Now by fine tuning, increasing the value here, I'm able to get a gain of 1000 and input resistance of course is fine. The output is at 0 volt here, but output resistance is almost 1K and I need 100 ohms. So the only problem that I'm left with is my output resistance is too large here. Okay, so what do I do now? How do I lower the output resistance? Lowering the output resistance will require you to lower this value here. And how do I lower it? All the things that you've seen earlier. So this is where we are here. So what it is saying is, I have an output resistance of around 1K, and this is primarily coming from this resistance getting divided by beta. primarily from that. Okay. So the idea is, if you want an output resistance of around 100, then you cannot have this resistance more than 10K, because 10K divided by beta will give you 100 ohms here. So as I said, why don't we go ahead and reduce 10K? So if you reduce it to 10K, then you will have to reduce this also to maintain the gain. So instead of 2K, it becomes 125 ohms. And then input resistance reduces here. And then what happens is, so I did that. So I went ahead and changed it to 10K, and we changed it to 125 ohms here. Look at that. I didn't change the differential pair here. First of all, my biasing gets upset. The output goes to now minus 2.92. Gain back to 595. I lose the gain here. And primarily coming, output resistance has fallen close to 150.6 here. But, this voltage is upset. The gain has fallen here. And the gain of the first stage is, the reason why gain has fallen is the gain of the first stage is decreased. Why? Because the first stage is getting loaded by the second stage here. The resistance has been decreased. So now one may think, well, why don't I lower this also? Why is this stage getting loaded by the second stage? Because the input resistance is much larger than this value here. It's not much larger than this value here. So can I really reduce RC1? If I reduce RC1, what will happen to the drop? The drop will change. Okay, so it's not as simple as that. So suppose I just take 20K here and I reduce it to 2K. I don't get any gain at all in my circuit. The whole circuit goes haywire. All biasing gets upset. In fact, this goes 11.9. There's no current here, no current here. So it doesn't work out that I can disturb this particular stage here and thereby, get it to work. So this particular strategy is not working. That I reduce this to 10K here, I reduce this voltage here to maintain gain, then this stage gets loaded here, and I can't simply reduce the value. Okay. So back again, this is where we are. Okay. This is the stage where we are, and output resistance is large. And so what we do is the following. A problem is with the output resistance. And what we try to do is, this is a common collector, and we think, why don't we replace it by this stage? All of you have seen this particular stage. It was a mid-sim problem also, that when you build a stage like this, Darlington stage here, then the output resistance looking from here becomes what? Here it is RS divided by beta, and in this case, it's basically RS divided by beta square. So the idea is, why don't I use this particular stage here? And therefore, my entire output resistance problem will be solved. Okay. So the idea is replace the normal common collector by a Darlington pair transistor with a normal 10 milliamperes. Now, when I do that, note that what happens is, we have chosen 160K, keeping in mind that there's a certain amount of base current that flows in, right? And we had fine-tuned this value here. Now, when I put a Darlington pair here, the base current that flows in is negligible here. So it requires us to retune this particular value. You don't require 160K, now you require 137K here. So I'm showing you a design here where 10 milliamperes with the Darlington pair transistor here, and this is getting upset here with 160K. With 160K, this value again goes to 10.195. So we have to retune this value here, and we bring it to 80K. If we bring it to 80K, this value goes back to 0 here. It goes back to 0 here, and we get the right as far as biasing is concerned here. But then we had to reduce the value of RC2. And what happened is that the gain falls to 630. So we get an output resistance which is now very small. Note that output resistance is 13.3, and gain has fallen back. So we had obtained a gain value with 160K, we had obtained a gain value which was close to 1000, and now we are back to gain which has become less here. So now that we have satisfied input resistance, we have satisfied output resistance here, but the gain has fallen here. So now the issue is, what do we do? Where do we go in order to build a higher gain? Note that I cannot increase this anymore. If I increase this, then it upsets my biasing here. So I can't increase this, and if I can't increase this, I have to leave this unchanged. If I leave this unchanged here, then everything else is unchanged. So we are stuck at this particular point with a gain of 630, output resistance of 13 ohms here. So the issue then is now think of something new. This Darlington pair is not working out for us. So one possibility is, now at this stage you can think of one possibility is as follows here. So I go back to my default design, which is here. This was a design, and I was trying to solve the output resistance problem by putting a Darlington pair here. But think about this possibility here. The other possibility was that you reduce this resistance to 10K. But if you reduce this resistance here, we were seeing this resistance falls and this one also, there's a problem that occurs here. Okay? So now there are two approaches to us, before us. One is we keep the design of the first stage and the second stage as it is, and we make a Darlington pair here. We lower the output resistance, but we lose the gain. Gain is no longer 1000. The other alternative is, so it's not working out. The other alternative is, we need an output resistance which is 100. So we lower this to 10K. We lower this value here. We can get a gain from this stage, but this one stage is loading the previous stage here. How do you prevent loading? This stage loads my previous stage here. So what I do is, between this stage and this stage, I introduce one more stage here. And what kind of a stage? Common collector. Another common collector stage here. Note that what I do is the following here. Can you see the rationale for doing it? I have lowered this value, 10K. This is going to give me the output resistance here. When I lower 10K, I have to lower this value here, RE3. And this RE3 is lowered, but then in between, we have put a common collector stage. Why? Because when I look into the base here, I don't see this particular stage here. I see a common collector stage, and common collector stage has a higher input resistance here. So that's why we insert one more stage here, a common collector stage, as a buffer between differential pair and a gain stage. And this is going to provide me, will raise the input resistance here. Note that I don't require a gain from this stage. The only goal of this particular stage is to increase the input resistance to a sufficiently large value here. All right. So then the strategy would be to proceed with 10 milliamperes biasing with 10K here. We reduce the value here to get adequate gain, and we design a common collector amplifier to build enough input resistance here so that my differential pair doesn't get loaded. Okay. So this then becomes at least a promising path, and we have to see how well it works. We have to choose the value of RE2. We have to choose the value of RE3. And do the design here. So coming back, the gain of this particular stage we had seen here is a drop here at this particular point, and the drop here, 11.3. And so we require this to be 0. This will be 0.7. And what we do is we set VE3 here to be 11.7 at this point here, because the voltage gain depends on this ratio here. So we set this to 11.7. Which gives us a gain of this particular stage as 37.66 and RE3 as 265 ohms here. So this decides RE3. Once we know this 11.7 here, then we know this is 11.7, so this is 11 here, and if this is 11 here, this becomes 10.3 here. So 10.3 here, so the drop from here to here is 12 minus 10.3, so which is 1.7, and we know the collector current, so that gives us a new value of RC, which is 34K. And AV1 then comes out to be 32.7 here, the gain of the first stage here. The other thing is, we have to make sure that the input resistance here is much larger than RC here, so we make sure that beta times RE2 here, beta times RE2 is much larger than RC. So that tells us that RE2 should be much larger than 340. So we choose RE2 as 3.4K. So we have a design which is complete. And if we simulate it here, if we simulate this particular design, we get, biasing is a little bit upset here, -2. So we tune this value here, a little bit tuning. And we get a biasing which is close to, so going from 10K to 9K, a little bit of tuning brought the biasing to a proper value. And gain is 1155, output resistance is 83, input resistance is 115. So everything satisfied here. So we get a gain of 1000. We get a gain of 1000, more than 1000. Output resistance is there. Yeah, so let's stop here. Design of the op amp is not complete, so let's stop here.